Imagine a car traveling 100 miles over the course of 5 hours. Standard arithmetic gives us a clear result. Divide the distance by the time, and you find the car moved at 20 miles per hour. But the actual journey is rarely that consistent. You speed up down hills, stop for red lights, and crawl through gridlock. The 20 miles per hour figure is just a macro-level summary. It's a blurry overview that fails to describe the car's behavior at any specific, frozen point in time. This raises a specific question. How do we determine the exact speed of the car at one precise coordinate on the road? Measuring speed requires a change in position over a change in time. But in a single, frozen instant, the car travels zero distance and zero time passes. Because we cannot divide by zero, our standard tools for calculation fail here. To find the speed of a moment, we need a different approach. We can start by shrinking the window of measurement. Imagine a policeman setting up a speed trap that monitors only a tiny 4-mile stretch of the road. If the car covers that stretch in 3 minutes, the officer calculates an average of 80 miles per hour. This is a much closer estimate of the speed at that specific location. However, it's still an estimate. Within those 4 miles, the car could have accelerated from 70 to 90. The average of 80 hides those fluctuations. No matter how small the distance, we are still just looking at an average. To find the true speed, we have to keep shrinking the window. We could try to shrink the window until the distance and time are effectively zero, but dividing 0 by 0 results in a mathematical error. The logic of standard division collapses when we try to freeze time completely. To find a way around this, we can use a controlled model, a falling ball governed by the equation distance equals 16 times time squared. Our goal is to find the exact speed of this ball at the 2-second mark, without triggering that zero division error. Instead of 0, we look just after 2 seconds. Over 1/10 of a second, average speed is 65.6. At 100th, it becomes 64.16. At 1000th, 64.016. The values converge toward 64. In mathematics, this destination is called a limit. It is a value that a variable approaches and stays close to as the interval shrinks. By identifying this limit, we found the true speed of the ball at exactly 2 seconds, 64 feet per second. We can translate this process into algebra by using the letter h to represent that microscopic, shrinking interval of time. When we plug h into our falling ball equation, the math simplifies elegantly. The terms cancel out, leaving us with 64 plus 16h. As the interval h shrinks toward nothing, the 16h part becomes effectively 0, leaving a clean result of 64. This algebraic approach allows us to calculate motion without needing to measure a physical journey. We can now describe the exact rate of change at a single point, rather than across a distance. This calculation, finding the rate of change at a specific instant, is what mathematicians call the derivative. The derivative allows us to isolate how a value is changing at any single moment, even when that change is constant and fluctuating. Ultimately, calculus is the mathematics of zooming in. By shrinking the interval until the time elapsed is negligible, we move past the blur of averages to resolve the exact speed at a frozen coordinate.